Dear participants, kindly mute the audio. Uh,
Right.
dear, dear participants, please kindly mute your video and audio. A very good morning to all the participants who are attending today's webinar on thermal remote sensing and its application in hydrology. Now I am here to introduce Dr. Easwar Rajashekaran, Assistant Professor from IIT Mumbai. He is going to today give us a talk on thermal infrared remote sensing and its application on hydrology. I would like to give a short note on the speaker. He has graduated his BE Civil Engineering at Anna University, Guindy, and he has completed his PhD in Indian Institute of Science under the topic Modeling of Evapotranspiration for the Indian continent, and also he has completed his postdoctoral research at NASA, and he has been a peer-reviewed editor for many journals, and he has received many awards such as Gold Medal Award from College of Engineering, Guindy. Then he has received Best Outgoing Student Award, and he has received Journal Best Editor Award. Likewise, he has many recognition from the Society of Remote Sensing and Hydrology, and he has published 10 number of publications, and he is handling some 10 project sponsored R&D projects from ISRO and DST. Likewise, he is the sound professional and active professional in the field of remote sensing. Now, I request Dr. Easwar Rajashekar to take over the presentation.
So, good morning, one and all, and thanks, Dr. Vidyapriya, for introduction and inviting me to this seminar. And I'm glad that even during this lockdown, like everyone is interested to listen to technical webinars, and I'm also happy that I can contribute to some knowledge sharing. So here, as Dr. Vidyapriya pointed out, I'll be discussing briefly about thermal remote sensing. Thermal remote sensing essentially has received much attention, especially like in our country. When most of us learn remote sensing, we learn about optical, we learn about microwave, and then stop at that particular point, whereas thermal remote sensing has not received much attention. So that's why I thought like, okay, we can give a short introduction to it. So before going to the presentation, I'll try to be as non-technical as possible because it's an online webinar. I know people will be having difficulties in listening, then maybe internet breaks and all those things will be happening. So I'll try to be as non-technical as possible. If you have any questions, even in between, please feel free to stop me and ask questions. So let us have this discussion as lively as possible rather than a lecture. I'll be happy to interact with you rather than like being in a classroom mode. So let me share my screen. Yeah. Okay. So I guess all of you are able to see my screen. Okay. So, okay, as I said, this topic, the presentation will be about thermal infrared remote sensing. So basically, before we go even to touch remote sensing, we'll just revisit some energy transfer mechanisms because essentially, thermal infrared remote sensing as well as its application is nothing but finding out how heat is transferring itself between different mediums such as land to atmosphere. And also I just wanted to give a brief revisit of what we have learned in our school physics classes. So heat energy can basically transform from one point to another through three forms that we all know: conduction, convection, and radiation. So conduction is direct heat transfer through the solid mass. Say like we are heating something as shown in this figure. 1 second. Yeah. So as shown in this figure, say if we heat something over this vessel, then the heat will be transferred towards this handle that we normally experience in our kitchen. We use kitchen cloth to hold hot vessels from directly taken from the stove. So that kind of process is conduction, where heat is transferred directly within the medium or through the medium directly. Convection is another simple process which takes place within fluids, basically liquids and gases, in which heat molecules, when it is being, say for example, we have a water in this vessel, heating will happen from the bottom. So the water molecules will start moving upwards, and then colder molecules from the top will come downwards. So this will kind of set up a random motion within the heating medium. Same thing happens in our atmosphere every day. Like when land heated up, air gets heated up and moves upwards, that we all know. That process is convection. And radiation is, uh, which is a form of energy transfer or heat transfer, basically, which doesn't require any medium. Say like we heat up during cold nights, we used to heat up our home using like some thermal radiators or using some heaters, where the heat will be distributed in form of like radiation without having any medium. Like if we go near a hot furnace, we feel the heat without even like coming in physical contact with the medium. So all this is radiation. So principally, the major form of heat transfer occurs in the Earth's surface through the process of radiation and convection. So, so in remote sensing, basically what we do is we use this radiation energy. So what exactly is remote sensing is? Remote sensing is kind of like a technology in which we obtain information about some feature without in physical contact with it. So this definition we should be knowing from our basic remote sensing classes. Just as a refresher, I'm telling you. So what we normally do, say for example, we need to have some experience about some objects in the earth. We take some imagery of the object, and the imagery will contain some information about the object, primarily through like a signal from a radiation perspective. So that's what this remote sensing is. So we collect some data, analyze the data, and from the data analysis, we try to get some information from the object or phenomenon. And essentially, the collection of data is nothing happens through a non-contact form without being in physical contact. So very good examples of remote sensing is like how we see basically. The process of our vision itself is a very good example for doing remote sensing. Like sunlight or whatever light source we have radiates itself through the atmosphere, falls on our object of interest, and it gets reflected back, and we see it through our eyes. So essentially, our eyes acts as a sensor. The sun is the source of energy which radiates energy. Here the energy comes out in form of radiation. It falls on the object of interest. It gets transferred again in form of radiation, and our eye sees it and our brain senses it. So essentially, this is like how typically remote sensing happens. Even when we do satellite remote sensing, same thing happens. Sun is the source of energy, it falls on some object, but instead of we seeing it, a satellite sensor sees it, and then later we analyze that particular data to get more information about the object of our interest. So as I described in the previous slide, some form of energy is required to collect information about the object, and that particular form of energy is what we call technically as electromagnetic radiation. As I said before, radiation is one form of energy which doesn't even require any medium to propagate from point A to point B. So the radiation travels from sun to the earth, and from the earth it interacts with whatever objects is there, and then finally reaches the satellite sensor basically. So electromagnetic radiation is nothing but a way in which energy propagates. Maybe we will not go into technical details about EMR and all, but just you can remember that EMR is kind of a way in which energy propagates. That's all. So what exactly is EMR? Some basic things we need to know. So maybe again in school physics classes, we would have learned that radiation or energy transfer can happen either in form of a wave or in form of like a photon, like what is it, quantum physics theory, as well as like Newtonian theory we have learned. So basically, when it travels through waves, this is what we normally consider like radiation transfers in form of waves for most of the applications. So each wave will have a characteristic wavelength. We know what wavelength is: distance between two crests or two troughs, or between one crest and next trough, whatever it is, we call it as one wavelength. and frequency, how many cycles per second the wave go through, that again we know. And one thing we have to remember is the energy of a wave is directly proportional to its frequency. That is, higher the frequency of the wave, higher will be its energy content. So
Hello, sir.
this,
Hello,
hello,
sir.
hello,
Easwar,
yeah,
Easwar,
yeah,
sir.
yes,
The
I'm hearing.
the slides are not changing, sir. That is the request from the participant.
Slides are
Again,
not changing.
yes, sir.
Okay, right now, can you please tell me the slide, which slide it is
Only
showing?
only the first and the first slide are showing.
So it is first slide, sir. It is an introduction slide.
Same slide only it is available.
Oh, sorry, I don't know what's happening.
Yeah, that is when we called you, sir. Yeah.
Okay, okay, fine, okay, fine. I shared my screen, but what happened? My meeting shows I am presenting the screen to everyone.
So your screen is visible, sir, but it is in first slide. Yes, sir. Now it is okay.
Yeah, now it is okay. Yeah, yeah.
Okay, I think when you put slideshow, something is happening. Okay.
You can proceed, sir. You can proceed.
Okay, okay, fine. Okay, fine. So sorry for this interruption. I didn't know that
No
slides are
problem.
not changing.
Yeah, yeah,
Yeah,
yeah.
okay.
Yeah.
Okay, basically, so what initially was covered is like giving EMR and all. So this is where we are here. If I go to slideshow now, can you see me, sir?
Yes, sir. We are able to see. Yeah.
Okay, that's good, because if I want to point something, it will be better. Okay, fine. So as I said, electromagnetic radiation is kind of energy transfer mechanism. So something. Sorry. Yeah. So one thing we have to remember is the energy content of a wave is directly proportional to its frequency. That is, higher the frequency of the wave, more the energy content of the wave. This is the only thing we have to remember. So the wavelength, frequency are inversely related. Similarly, energy and frequency are directly related. So this one thing, if you remember, that should be good enough for the presentation. Okay. Now the next slide, what I'm showing is the entire electromagnetic spectrum. Sir, has the slide changed? Just to confirm once more, I changed the slide.
Now it shows the electromagnetic radiation, sir.
Oh, okay. I think slides are not changing when I move the slide. Okay. Now can you see electromagnetic spectrum?
Yes, sir. Yes, sir.
Okay, I think when I put slideshow, I think it is not changing. Okay, I'll continue to present it like this only. Fine. Okay, so basically, what electromagnetic spectrum is, we just learned electromagnetic radiation is one form of energy transfer. So that can happen through a big chain of continuum. That is, radiation can have infinite wavelengths or infinite frequency levels. So that's what totally we call as electromagnetic spectrum. That is, we can have radiation propagating with a wavelength of larger than like a football field, like in order of hundreds of meters. And on the other end of the spectrum, we can have wavelength, or we can have energy transfer occurring with wavelength that is much shorter than a scale of an atom. So basically, the more shorter wavelengths we experience in nuclear reactors, radioactive elements, and so on, whereas the longest waves, which has a wavelength of in order of meters, we use it for our communication purposes, like radio transmission and all those things. So what exactly we use to see, or what exactly the wavelength we use to do remote sensing is somewhere lies here in this particular band of portion in between visible, infrared, and microwave. So remote sensing, we all know we do visible remote sensing, that is the visible white light, which contains three primary colors, red, green, blue. Similarly, just after the visible spectrum, we have this infrared spectrum. After the infrared spectrum, we use the microwave spectrum. So essentially, for remote sensing, especially for Earth surfaces, we use visible, infrared and microwave portion of electromagnetic spectrum for doing remote sensing purposes. And this infrared portion of spectrum can be further divided or subdivided, I can say. We divided into near infrared, short wave infrared, long wave infrared, and so on. So basically, thermal infrared remote sensing means we are going to do remote sensing in the infrared portion of the spectrum with the wavelength range of 8 to 14 micrometers, and that falls under the category of long wave infrared spectrum. Somewhere it will lie here. So where I am moving the cursor, hope you are all able to see. Somewhere it will be here in this particular wavelength range. We will be doing thermal infrared remote sensing. Okay, just few laws I would like to mention before we proceed further. Primarily, what is the source of this energy production? That's what we need to know. That is, we all know like sun is generating energy, we are sensing it. Similarly, earth is also creating some energy, we are sensing it in thermal remote sensing. So primarily, what exactly the source of energy? The major source in which energy is generated is through the heat content of the object. Like even in sun, the energy is produced in sun, we all know, by process of like nuclear fusion fission processes, which produces huge amount of heat energy. And only with respect to the heat energy, sun is releasing so much of radiation. Same thing happens with earth also. Earth also has some temperature to it or some heat energy content with it. We all know the earth center is still a molten lava, molten core. That helps the earth to get heated up in addition to sun's energy, and earth also will emit energy on its own. So basically what we need to know is whatever be the object, as the object's heat energy content increases, it will radiate more. This is one basic thing we need to remember. Like sun has like a very high temperature, so very high heat energy content, and temperature, even the outer surface of sun is around like 6000 Kelvin. So sun is radiating at a much higher rate or a much higher energy content. It is radiating. Earth's average temperature is somewhat around like 280 to 300 Kelvin, much lower than sun, but still by virtue of its energy content, it will also still radiate. So that is the basic gist of these three laws I am mentioning here. Here I am mentioning three laws: Planck's law, the most fundamental law in remote sensing, Stephen Boltzmann law, and then Wien's displacement law. So basically what we have to remember is, maybe I'll show it in the next slide. Oops, too fast. Yes. In this particular slide, what I have done is, it's kind of like I'm showing two plots, which tells that given object temperature, say like there are like graphs plotted for different objects at different temperature. Given an object at a particular temperature, what will be its energy release? So each curve, the area under each curve will give the total energy released by that particular object. So how it will vary with respect to wavelength, like whatever be the energy release, it will be in form of like radiation. Mostly it will be in form of radiation. That particular radiation energy, it will not have one wavelength. It will, as I said before, it's a continuum of wavelength. It will propagate with multiple wavelengths and multiple frequencies and so on. So basically, if we plot it, we can see it takes a form of like a curve like this, and the energy content the object releases will again vary with respect to wavelength. So as the temperature of the object increases, the total energy released by the object also will increase, and also the wavelength of the object with the peak energy will move towards shorter wavelength. Okay, so yeah, same thing is repeated here. Just to show between sun and earth, say this yellow curve with the labeled 5777 Kelvin. This is for sun, outer surface of sun. You know how the curve looks. And similarly, the red color curve at 300 Kelvin is typically for earth. That's what we experience at earth's surface. So sun is releasing at a much higher energy level. The total energy content of the sun is much higher. Similarly, the peak, the wavelength at which the peak occurs for sun is somewhere in between 0.5 micrometers. So here the peak occurs. That's the white light we see, the visible light we see. If you take earth, the peak energy release happens somewhere in the infrared portion here, somewhere here, around like between 9 to 10 micrometers. So the take home message from this particular slide is, as the temperature of the object increases, the total energy released by the object also will increase. Point 1. Point 2 is the energy released will be coming out with different wavelengths, and the maximum peak energy will occur at one particular wavelength for objects at different temperature, and that peak wavelength will become shorter and shorter as the object's temperature increases. That is, for Earth, the peak wavelength, as I said before, is somewhere around 9 to 10 micrometers in the infrared portion, much longer wavelength. Whereas for Sun, the peak occurs at 0.5 micrometers, much shorter wavelength. So as the temperature of the object increases, the wavelength at which peak energy release occurs also will go shorter and shorter. So this is the take home message from the slide. So why I explained all these things? Because these are all the basics for what we do as thermal infrared remote sensing. Like just to give like a brief thing. So Earth as an object has certain energy content. In addition to that, sun's radiation also comes and fall on Earth, which again changes the energy content of the Earth's surface. Because of that, Earth's temperature will change, and with that temperature, Earth will start emitting some radiation form. And from the basic laws we have seen in the previous slides, that particular energy release in radiation form will occur primarily in 8 to 14 micrometer bandwidth. So here I'm highlighting 8 to 14 micrometer bandwidth. And if we use some sensor to measure that radiation from the Earth and use that radiation to calculate the temperature of the Earth's surface, then we are doing what is known as thermal remote sensing or thermal infrared remote sensing in a more technical way. So essentially it is nothing but we are sending some sensors to the space. We are trying to capture what is the energy coming out of the Earth in this particular wavelength, particularly in this range. And from that particular energy that we sense, we try to calculate temperature of the Earth's surface, and we use that particular temperature in various applications. So this temperature that we calculate from space is known as land surface temperature. And the particular process of sensing this energy and calculating land surface temperature and using it for various applications is broadly known as thermal infrared remote sensing. So essentially it is kind of like a simple process of what a doctor does. Like when we have fever and go to a doctor, the doctor will take a temperature reading and say like, okay, this is and diagnosis what is happening. So this can be the reason for the illness. The doctor will prescribe some medicine. Same analogy can be taken here. Earth has some temperature, it will radiate some energy. We sense that energy, calculate the temperature of the Earth's surface. From that, we get to know more information about the Earth's surface. Because whatever happens on Earth's surface will change the temperature, and that temperature will be used by us to know more about Earth's surface. That's it. So this is the very simple analogy we can give for thermal infrared remote sensing and what normally a doctor does when we go with a fever. So just one more technical term I would like to introduce, that is known as emissivity. What exactly emissivity is? We have seen three laws in the previous slides. We have seen some basic curves like we have seen these particular curves which tells us how an object will radiate energy when the object is heated to different temperature. These curves we saw. All these curves are essentially drawn for objects that are known as black bodies. So what are black bodies is? A black body is kind of like an object which can emit with maximum efficiency as defined by thermodynamics. That is, say these laws are here. So basically these laws are being defined by physicists who experimented in using thermodynamic principles. So what essentially these laws says, if an object is at a given temperature, a total certain amount of energy will come out. That is what these laws says. This Planck's law and Stefan Boltzmann law. But these laws are applicable only for objects which are 100% good emitters, or we call it as black bodies. That is, they can emit radiation with maximum efficiency as defined by these laws. However, most of the objects on the Earth's surface are not black bodies. They are not very good emitters. They will not emit as prescribed by these laws. They have certain limitations. Say for example, we have two persons. One person, whatever, say for example, two persons are listening to some audio and they are telling something out to someone else to listen. Let us assume this hypothetical scenario. I have two persons, A and B. One person is, both the persons are carrying a headset on their ears, hearing something, and they're going to tell out whatever they are hearing. If person A is perfect, like he can tell whatever he's hearing, like so if person A is really perfect in telling whatever he's hearing out, then let us say that person can be classified as a black body. Whatever is getting inputted to him, he is outputting that. So input is equal to output basically. But let us take person B. Person B is not very efficient is telling. Person B is like completely forgetting everything within an instant. So whatever input he is receiving through the headset, he may not tell everything out. He may miss few things. Same thing happens with the Earth surface objects. Because whatever the energy input is being given to the object, that will not be released out by the object. It will have some deficiency. Say out of 100 units of energy received, an object can radiate only 95% of it or 90% of it. So that is what emissivity is. So real world objects cannot transform heat energy into radiant energy with maximum efficiency permitted by thermodynamics. That's it. So almost all Earth surface features are not black bodies. They are not black bodies. If you give 100% of energy to it, it will radiate back 95, 96, sometimes 90% of energy. So that is what we call emissivity. So based on emissivity, we can classify the objects, whatever objects, into three. One is black body, as I said, perfect emitters. Whatever energy is being inputted, it will give out. That is black body. Gray body is whatever energy is being given in, it will give out a constant, like less than 1, but it will remain a constant. Say for example, if you give 100 units of energy to an object, it will radiate 70% of energy and the 70% will remain constant. That is the gray body. Whereas the selective radiator is third class of objects, selective radiators. If you give 100 units of energy to it, it will radiate 10% at certain wavelength, it will radiate 50% at certain wavelength, and so on. That is, the energy output will vary with wavelength. They are selective radiators. And almost all features on the Earth's surface are selective radiators. That is, they will not emit energy with maximum efficiency, and the energy radiation also will change with respect to wavelength. So this is what is. So here, if you can see in this particular bottom curve, this curve, the top curve in which I'm moving the cursor is for a black body, a really smooth one, where emissivity is equal to 1. This is as described by Planck's law. So emissivity is equal to 1. The bottom curve, a bottom solid curve, is for a gray body. This also closely follows the black body curve in the same way, but with a lesser emissivity value. Maybe the emissivity is like 0.9 or something. Whereas this in between curve with dashes in it is a selective radiator. So basically, selective radiator is whatever be the energy input is, the energy output will vary with respect to wavelength. Say here in this particular wavelength, the energy release will be maximum. In this particular wavelength, the energy release will be minimum, and so on. So the amount of energy released will vary with respect to a wavelength for a selective radiator. And this is the problem we face for Earth surface objects, because all Earth surface objects are primarily selective radiators. So here also we can see water is the closest feature on the Earth surface that resembles a gray body. So water has more or less constant emissivity of 0.98, and hence water is a very good example for a gray body. Whereas most other features, say minerals, rocks, soil, whatever present on the Earth's surface, they are selective radiators. Their energy release will vary with respect to wavelength. Okay, maybe like now it may be really confusing to some of you why these things are really important, but later I'll try to explain why these things are needed for us. Okay, so in the introduction slides, what I told you all is like the energy that we are sensing in the 8 to 14 micrometer wavelength range is primarily from the Earth's surface. This particular slide is going to explain or is going to just substantiate that claim. That is, uh, this particular dotted curve, I hope all of you are able to see. This particular dotted curve is what the energy coming in from the sun, just truncated to a certain wavelength range. And then this dark curve is what reaches the Earth's surface. That is, this dotted curve is what it reaches top of the Earth's atmosphere, and this dark black line is what happens to it when it reaches the bottom of the Earth's surface. So what essentially happens, almost zero energy is coming from the sun in this particular wavelength, 8 to 10 micrometer or 8 to 14 micrometer range. So no energy is reaching the Earth's surface from the sun in this particular bandwidth. So whatever the energy we sense in this particular bandwidth from satellite sensors is primarily due to Earth's own radiation. So this is what I wanted to tell you. That is, whatever reason or whatever energy we sense in this particular wavelength, we calculate the surface temperature of the Earth, and from that we are going to use it for different applications. Okay, so is it really simple to measure the energy from the coming out of Earth's surface? No, it's not, because whatever the energy is coming out of the Earth's surface is being modified by the atmosphere, and that is the major problem. Second problem we encounter. First problem we will encounter is emissivity effect. Second problem we encounter is atmospheric effects. So what really happens is, say here we have the Earth's surface. It emits some energy based on its temperature T. It emits some energy. So this is what we call the energy emitted from the Earth, and really we need to measure this component, the first component, this particular component we need to measure. Only when we measure this, we will be able to calculate the temperature T, and from that we can use it for different applications. But we also have a gaseous atmosphere above us. What it does is, atmosphere also has some temperature on its own, and that will also emit something directly to the sensor. So that is this, what is known as atmosphere emitted component. One more thing what atmosphere will do is, atmosphere will emit some energy towards the Earth's surface, that will again be reflected back by Earth's surface. So what essentially happens is, atmosphere being present in between the Earth's surface and the satellite sensor somewhere up in the sky. So what essentially happens, atmosphere emits some energy, and that energy interacts with the energy coming out of the Earth, and it's kind of pollutes the signal that we need to learn, that we need to sense basically. So atmosphere is kind of like a pollutant to the energy that we need to sense. Only if we sense this term, LEU term, we will be able to calculate the Earth's temperature. But atmosphere kind of pollutes it, and we need to remove this particular effect of atmosphere in order to calculate this temperature. Fine. Till now I was telling temperature of the Earth's surface, temperature of the Earth's surface, but there is no real single definition of temperature. There are multiple definitions of temperature, and just for like a quick clarity, I would just like to touch different definitions of temperature that we have heard about. The first temperature that we normally measure is what is known as a true temperature or a thermodynamic temperature. So what essentially happens, say the same analogy of a doctor and a patient with a fever we take. What the doctor will do, the doctor will take a thermometer, they will insert it underneath our tongue. They will ask us to keep it there for some time, maybe like a minute or so, and then they will take the thermometer out, take a temperature reading. That's what people will normally do to measure temperature. That particular way of measurement of temperature is what we call a thermodynamic temperature or a true temperature. Basically what happens there, a thermometer is placed in the medium of interest, that is our own body. It's placed under the tongue, and the doctor keeps 30 seconds to 1 minute time. Why the 30 seconds to 1 minute time is given? Because the thermometer will be at a different temperature when it's taken out of its ice bath. our body will be at a different temperature. So the thermometer will need some time to come into a equilibrium with our body. Then only it can show the real temperature. So the thermometer will kept in physical contact with us underneath our tongue. It will take some time to come into a thermal equilibrium. Okay, that is to the same temperature. Then it will show the correct temperature. So if the doctor doesn't give that 30 seconds to 1 minute time, then the thermometer will not be able to measure or come into thermal equilibrium with our body. It will show a wrong temperature. So this particular definition of temperature is what is known as thermodynamic temperature. That is, we take a thermometer, keep it in physical contact with the object of interest, give some time for the thermometer to come into thermal equilibrium, then measure the temperature. This is thermodynamic temperature. We normally measure in hospitals. For Earth's surface also we can do that, but it is not really feasible to measure a thermodynamic temperature for Earth's surface, especially during daytime. Because during daytime what happens is, sun's radiation is continuously coming, Earth's surface will be keep on heating up, air will flow, lot of processes will occur, and the thermometer on the Earth's surface will never come to a proper thermodynamic equilibrium. So this kind of measurement is possible, but strictly speaking, by physical laws, we cannot do it, but we can do it to some approximation. So thermodynamic temperature is what we measure with respect to a temperature. Okay, fine. What temperature we are seeing here in this particular presentation, what I told you as land surface temperature in the introduction slide, is actually not the same thing as the thermodynamic temperature. That is, I'm sorry. That is, instead of like keeping a thermometer, what we are doing, we are keeping some sensor up in the sky. Let's say the sensor is now brought to Earth, kept close to the land surface without in physical contact. That will measure the radiation coming out. From that radiation, it will calculate the temperature of the Earth's surface. So essentially, the temperature we measure by this indirect way, that is without coming into physical contact, we call it as technically as radiometric temperature. That's what is given here. So technically this particular temperature is radiometric temperature, and that is not equal to thermodynamic temperature for Earth's surface. That's what is given here. So if you like have two different thermometers, one is a physical thermometer which you can place in contact with Earth, and another sensor which you can keep slightly away from the Earth and measure its energy coming out. When you calculate temperature from both these things, most likely they will not be equal. They will be equal only under some strict conditions, which I leave it for later discussions. So these two definitions of temperature exist. So the key take-home message what I wanted to convey is, the temperature that we measure from satellite is not equal to the temperature that we can normally measure with a thermometer. That is the only thing I wanted to say. These two temperature has different definitions. They have different applications. And one more question may come up in most of your minds, that normally we see in newspapers and news channels that air temperature is being reported. Okay, the Nungambakam Observatory has reported certain temperature. Meenambakam Observatory has reported certain temperature, 35 degrees Celsius, 30 degrees Celsius, and so on. These things we keep on hearing from news channels or we read in newspapers. Is it same as the land surface temperature? No, not at all. Air temperature, what we hear in newspaper is air temperature. That is, they will again keep a thermometer, but not with respect to land surface, but they will keep the thermometer in air 2 meters up from the surface. So essentially the thermometer will measure temperature of the air at that particular point. It will not measure the temperature of the land at that particular point. It will measure temperature of air at that particular point. So that is air temperature we are measuring. Whereas what satellite measures from this thermal infrared remote sensing is temperature of the land surface. What is there in the land? So air temperature and land temperature are related. They are related in some sense. If one increases, other also will increase, and vice versa under some conditions, but they are not one and the same. So here I have told you three different definitions of temperature. One is temperature we measure with respect to by using a physical thermometer, that is true temperature. Second thing is air temperature, that is what we here in newspapers, or sorry, here in news channels, read in newspapers. And third thing, this radiometric temperature we measure from satellites. All the three are different, they are not one and the same. So then what is the use of this particular temperature we measure from satellite? Maybe later I will tell you with an example. Okay, maybe I'll directly move to this particular example. Let us say a small area. A small area has two objects. I'm just telling two black bodies. So one object is a temperature of 293 Kelvin. Object 2 is having a temperature of 323 Kelvin. So what exactly happens? Some small area is there. Two objects are present in that particular area, each covering half of the area. Say we take 1 square meter. Half a square meter is occupied by object 1 with 293 Kelvin. Second half square meter is occupied by object 2, 323 Kelvin. So if I ask you to measure the temperature of that particular 1 square kilometer with a thermometer, what we normally do? We will go there, we will see there are two different objects. We will put thermometer on both objects and take an average. Simple. That is the average temperature of that 1 square meter area. So if you take average of these two temperatures, that comes out to 308 Kelvin. So this is the average temperature of that particular 1 square meter area when measured with a physical thermometer. Now, instead of giving you a physical thermometer, I give you like a small, say, a remote sensing sensor in your hand, a very small hypothetical sensor. We take the sensor, we keep the sensor somewhat at a higher level from that 1 square meter area. We measure the radiation coming out of the object. The radiation coming out of the object will be 517 watt per meter square. And if we use the three laws I've told you before, like say this particular law, these two laws, law 1 and law 2, if we use that, because from the energy content and temperature related by these laws. So what is doing this from these law and yes, from that law and this energy content measured by our remote sensing sensor, we can calculate again the temperature, and that particular temperature comes to be 309 Kelvin. So essentially what it says is, when a surface has two or more than two different mixed objects, then definitely the temperature measured by a physical thermometer and the temperature measured by such distant remote sensing sensors are not one and the same. Here the physical temperature is 308 Kelvin, whereas the radiometric temperature is 309 Kelvin. This is like the simplest example I can say. In real world, it is much more complex. We have buildings, we have trees, we have soil, water bodies, everything on the land cover. And hence, whatever a satellite will see at a certain pixel level will have more number of land cover features, and it's really difficult to measure a single temperature out of it. Okay. Fine. So till now what we have discussed is all basic laws of thermal infrared remote sensing, what thermal infrared remote sensing is. Now we will slowly move on to how we really calculate the temperature of the surface and what we use for it. So that's what we are going to see in the remaining slides. So the first thing is, first of all, how we can calculate temperature of the Earth's surface from satellite observations. So what essentially satellite does is, satellite is going to measure the energy coming out of the Earth's surface, and from that energy we are going to calculate temperature of the object. Very simple as it can sound, but it's not as simple as it is. It is one of the most complex things that we do. So what happens? I just introduced to you the concept of emissivity, which will vary with wavelength. First thing. Second thing is, I just briefly introduced what atmosphere does. Atmosphere kind of pollutes the signal from the Earth's surface. It adds something more to it or absorbs something out of it. So essentially, two effects are there. One is effect due to atmosphere. Second thing is effect due to surface emissivity. These two things we have to remove from the signal. These two effects we have to remove from the signal seen from the satellite. Then only we can calculate the true temperature of the Earth's surface, right? First, we will see how we remove this effect of atmosphere. Just very briefly, I will just mention and we will pass on. First thing, the process of removing the effect of atmosphere and remote sensing signals is what we technically call as atmospheric correction. So that is, we are now going to correct the signal for atmospheric effects. How we normally do it? So essentially, we need to have what is known as a radiative transfer model, that is RTM, a radiative transfer model. So what essentially radiative transfer model do? It's kind of a complex model, really like a complex computationally demanding model. So what it will do? It will have all basic physical and chemical laws embedded within it. It will calculate, okay, if this is the percentage of oxygen, if this is the percentage of CO2, if this is the percentage of water vapor, then how much atmosphere can emit, how much atmosphere can absorb, all these things it will calculate. So essentially, a radiative transfer model will try to simulate how atmosphere will behave in absorbing or emitting radiation. That's it. So what we need to measure or what we need to do, we do satellite remote sensing. At the time of satellite overpass, say each satellite will come overhead at a certain instant of time. Let us say the satellite is coming now at around 10:30 in the morning. Then at that particular time of satellite overpass, we need to measure the air temperature at different heights. We need to measure the water vapor content of atmosphere. We need to measure CO2. All those things we need to measure. People will send balloons up in the sky. Those balloons are known as radio sound. Like they will send balloons up in the sky carrying multiple sensors. The balloon will slowly go up into the atmosphere, measure whatever is needed for it, and then it will finally come down after say 30 minutes or 1 hour. So this is known as a radio sounding. So people will measure all these things with a balloon, feed the data into a radiative transfer model. Some of the radiative transfer model is given here, Montran, RT tau. These are some basic things. So from this radiative transfer model, we can calculate how much effect atmosphere has basically. And one such model is there available in internet. Maybe for people who are interested, I will tell later how it is done, but right now I will just leave this. Okay. And this slide also I just leave it just for the sake of time and the clarity. Okay. Now, so this simple radiative transfer model can be used for correcting the effect of atmosphere. So the radiative transfer model will essentially give, in this particular equation, if you take, it will give this particular variable. Okay. What I should do. Okay. Here in this particular slide, the radiative transfer model will essentially give us this RATK term upward, this RATK down, this tau term, all these technical terms will come from this radiative transfer model. We need to calculate surface emissivity on our own. Then if we know all these things, this effect of atmosphere and emissivity, then we can calculate the temperature of the Earth's surface using the energy sensed by the satellite. Okay, fine. Now let me move to a simple example to tell how much effect atmosphere has and how much effect a surface emissivity has. Maybe I've given a lot of data in it. Basically, in this particular problem, what I wanted to convey is some satellite. Here I've given example of Landsat 7. A satellite measures some energy coming out of Earth's surface, and for two different pixels, each having some emissivity value. Like pixel A has emissivity of 0.9, pixel B has emissivity of 0.95. Then we somehow get all the atmospheric effects. Only one thing we have to do is calculate the temperature of the object on those two objects A and B, with and without the effect of atmosphere and emissivity. That's it. So in this particular example, my major aim is to tell how much effect atmosphere and emissivity can bring into our calculations. That's the only aim. First, if I do everything correct, like if I do everything based on physical laws, that is, I am correcting for atmospheric effect, I am correcting for a surface emissivity effect and all those things. Then for pixel A, I get a temperature of 318 Kelvin. Similarly, for pixel B, I get a temperature of 315 Kelvin. So this is the temperature after correcting for atmosphere and emissivity effects. Just remember these values: 318 for pixel A, 315 for pixel B. Now, if I if I do not take the effect of emissivity, or if I take only the effect of emissivity into consideration, then what I will get is, for pixel A, I am getting 302 Kelvin. For pixel B, I am getting 308 Kelvin. So essentially, this itself is wrong. The real temperature is 318 and 315 for A and B. But if I neglect effect of atmosphere and I take only emissivity effect into consideration, I am getting different values. Instead of 318, I am getting 312. Instead of 315, I am getting 308. If I neglect both emissivity and atmospheric effects, then we will get 304 Kelvin as the temperature. So essentially what we can get is, we must take into account the effect of atmosphere and surface emissivity, and if we miss it, then we are going to have a lot of errors in calculating the temperature of the object. So this is the only thing I wanted to convey. Other than this, what I wanted to tell is, rather than this effect, also the angle in which the sensor sees the land surface will have an effect on it. That is what we call as directional anisotropy. Maybe again I neglect or leave this particular term for later effect. Okay, all these things are basically theoretical aspects. Okay, what we can really get, from which satellite we can really get the data out of it. Maybe some satellites I have listed here. Some satellites which can measure the temperature of the Earth's surface I am listing here in this particular slide. One satellite is MODIS, most common. Most of the people working in remote sensing area would have heard this MODIS satellite, which will give a pixel resolution of somewhat around 930 meters. And almost every day we will get one data. So every day, at least one data will come from MODIS sensor. Then there is another sensor called VARS. Again, it will give us data with 750 meter resolution. That is, each pixel will roughly have a size of 750 meters by 750 meters. Again, it will give data every 1 to 2 days. There are different satellites. Say Landsat 8, it will give data at 100 meter resolution every 16 days once. Then over India, we have satellites in geostationary orbit like INSAT 3D and all, which will give data every 30 minutes, but with a spatial resolution of 4 to, now we are getting at 4 to 5 kilometers. Olden days we are getting 4 to 8 kilometers. So roughly what it says is, there are different satellites which can measure temperature of the Earth's surface. That is available. But only thing, if you see in this particular slide, as the spatial resolution becomes smaller and smaller, the number of days or the temporal resolution is going in a larger and larger direction. That is, say Landsat 8. Landsat 8 will give us data at 100 meter resolution. That is, each pixel is just 100 meter by 100 meter. But we can get data only once every 16 days. On the other hand, MODIS, resolution of around 1000 meters. It will give data almost daily. Geostationary satellite, resolution of 5000 meters, 4000 to 5000 meters. It will give data every 30 minutes. So what is the essential message from this slide is, when the spatial resolution of the thermal sensor becomes smaller and smaller or finer and finer, the number of days for the number of days in which we have to wait increases. So essentially, if I need a very fine spatial resolution data, I need to wait for 16 days. If I can live with very coarse data of say 4 kilometers or 5 kilometer pixel size, I can get once every half an hour. So this is what we call as trade-off, a trade-off between spatial and temporal resolution. If you want high spatial resolution, we have to sacrifice temporal resolution and vice versa. However, for most of the applications, one application I'll tell later, evapotranspiration modeling. For such kind of applications, essentially we need data at 100 meter resolution at least once a week. I'm telling you here, at least. If we get data more than once in a week, that is really good. But we need data at a spatial resolution of 100 meters, because for whatever be the applications, be it studying the effect of urban areas, be it studying the effect of agricultural applications, how much water is needed for crops, all these things needs very fine spatial resolution data. Because if we go out and see, we can see that India is a really dense country with lot of different landforms. Our agricultural lands are smaller, our buildings are kind of like closely spaced to each other, and not like Western countries like US and Europe. So for applications, especially over Indian context, we really need data with a high spatial resolution in the order of 100 meters, and that data should be available at least once a week. However, we don't have such satellite sensor available at present right now. If we need fine spatial resolution, then we need to wait at least 16 days. Is there a way to uh, come over this particular drawback? Yes, we can do. Like a lot of scientists in thermal remote sensing, they normally do what is known as data disaggregation or data fusion. So essentially, to put in a very simple term, data disaggregation is nothing but artificial way of increasing the spatial resolution of a satellite data. That is, I give you a data of 1000-meter resolution. I give you some more additional information like what is the land cover there, what is the vegetation cover over there. Such information I give you. These are all we call ancillary data. So using this particular information, if we can get the 1000-meter data to say 500 meters or 200 meters resolution, that particular process is what we call disaggregation. This is possible. Currently, we are trying this particular things in our lab in IIT Bombay. So how to improve the spatial resolution of thermal resolution satellite. Another particular process is what is known as data fusion. Data fusion is commonly mixing data from 2-3 different sensors. Say I mentioned different satellites to you. Say we will take, this is the MODIS sensor. It will give you image every day at a spatial resolution of 1000 meters. Then comes Landsat. It will give you image at 100-meter resolution every 16 days. Can we combine these two data of two different sensors and create 100-meter data every day? So that is, I am synthetically or artificially generating fine resolution data every day. This process is known as data fusion, merging data from 2 or more sensors and creating artificial data sets. This is data fusion. So data disaggregation and data fusion are some of the commonly used techniques to improve the spatial resolution of thermal sensors. So this is kind of one of the most important exercise we are doing in our group in IIT Bombay. Maybe like those who are interested can discuss later. Okay. So now we move to the applications part. Till now what we have learned is very basic theory to thermal remote sensing, what exactly thermal remote sensing is, and so on. So I'll just quickly give what is its major application. Just for want of time, I think we have 15-20 minutes more left. So just I'll briefly mention the applications. Okay. So essentially, as I said in the first examples, introduction examples, thermal infrared remote sensing is kind of like a sensing the temperature of Earth's surface and using it for different applications. The applications can be in the field of hydrology and water resources. That is basically trying to calculate how much water is being lost from the Earth's surface. We call it as evapotranspiration. How much water is lost to the atmosphere. We can calculate that. Second major application area is agriculture. So agriculture is, again, how much water is lost from the crops, how much we should irrigate the crops, is the crop really healthy or it is undergoing some kind of stress. All those things we can calculate using thermal remote sensing data. One more major application is urban heat and studies. That is, whenever a new city is coming up, that particular city will exhibit a higher temperature pattern than its surrounding rural areas. We call it as urban heat island effect. And one of the most widely used application of thermal remote sensing is studying this urban heat island phenomena, because as the heat of the city increases, as the temperature of the city increases, it may cause discomfort to the people living there, or it may increase the demand for air conditioning and so on. So people generally study how hotter a city is in comparison to rural areas and how to mitigate that. So all these are different applications of thermal infrared remote sensing, that is to measure the temperature of Earth's surface. So here what I'm going to basically talk about is how to use it for hydrology. Basically I'm going to tell how I have used the data for calculating evapotranspiration. Very simple. So essentially, to put simply, evapotranspiration is nothing but the transfer of water from the Earth's surface to atmosphere in form of water vapor. That is, when we boil water, water gets converted from liquid form to vapor form and goes up. We all might have seen it. This also occurs in nature. Every second, some amount of water is getting transferred from land surface to atmosphere in form of vapor. That is known as evapotranspiration. And that is kind of like one of the most important variable to measure in hydrology and water resource application. So how basically to do it? Uh, Again, try to tell it in a simpler way. Sun's radiation is coming in. Some portion of the sun radiation, what will happen is, will be sent back directly by Earth's surface. Like that is what is given here in form of radiation. But some form of sun energy, what will happen is, it will be used to heat the water and transfer the water from liquid to vapor form. So some portion of sun energy used to heat the water and transfer to vapor form. Some portion of sun's energy will be used to heat the Earth's surface, and that will be used to heat the air molecules near the Earth's surface. So that is heating the land, and then land will be heating the atmosphere. So different things can happen. First thing is, sun radiation will come in this particular part where I'm moving the cursor. Sun's radiation will come in, heat the Earth, and again it will be radiated back. This is one portion. Second portion is, some small amount of sun radiation will be used to convert the water in the Earth's surface from liquid to vapor form. That is what we call it as evapotranspiration or latent heat flux, LE we call technically. Some portion of sun's energy will be used to heat the land, and land will be heating the atmosphere, and that will move up. This is what we call it as sensible heat flux. So essentially, this is the right hand side portion of the slide where I'm moving the cursor is radiation term. This particular portion of the slide, this sensibility and evapotranspiration or convection terms, basically. The very good example of sensible heat is, say, most of us would have traveled from our place of work or place of education to our hometowns in a bus or a train. Normally we do. When we would have traveled like that, we will feel like hot, especially on hot summer days, we will feel hot air coming and hitting our face. That is sensible heat flux. Land is heated up, that land is heating up the air, and that air is coming and hitting us in our face when we travel. And we can feel the heat, or we can feel the temperature. So that is what is known as sensible heat. We can sense sensible heat flux. On the other hand, if the energy is used to convert water from liquid to vapor form, we cannot see it or we cannot sense it. That is why we call it as latent heat flux. Okay. So essentially, one of the major application of this thermal infrared remote sensing is calculating how much water is heated up. I will directly move to this particular slide. Okay. So how essentially it works, how thermal infrared remote sensing in general works for measuring this. That is what is known as surface energy balance. Actually, I have skipped that part for the want of time, but I'll just tell you in a very simple way. Let us consider a dry land surface, say very dry surface without any water in it. Whatever sun's energy is coming in, it will directly heat the land surface, and the land surface temperature will increase. So if we use a thermal sensor, remote sensing sensor to sense it, it will sense a higher energy coming out of it and hence higher temperature. So a dry surface will have a higher temperature. On the other hand, if there is a small water body, or if you are irrigated the land, or if there is like a very good crop standing over it, then what will happen? Whenever there is water present on the land surface, we have just seen some portion of sun's energy will be used to convert the water from liquid to vapor form, and that energy is kind of lost. We cannot like get it back. So instead of heating the surface, the energy is used to transfer water from liquid to vapor form. So the Earth's surface is not heated there. Water is lost, but Earth's surface is not heated there. So whenever water is present on the surface, the temperature of the surface will not increase much. Then what will happen is the remote sensing sensor will see a lower temperature for that area. So basically, places that are really dry without any water content will show higher temperature. That is what is happening in like dry barren surfaces or in oval cities. Whereas land surface with water content in it, say we have irrigated or vegetation standing over it, then we will be sensing a lower temperature. And this difference in temperature we can use to calculate evapotranspiration basically. So this is one really basic example. So here I'm just showing a map of land surface temperature calculated for a small part of Kaveri River basin. So this particular white portion is the Kabini Dam or Kabini Reservoir. This is the Kabini River, and where it meets the main Kaveri, it forms the Kaveri River here. Here we have the Bhavani Sagar Dam. This lower portion is the Bhavani Sagar Dam. So this kind of like mix of Karnataka, Tamil Nadu and Kerala state, mix of 3 different states. And this is the land surface temperature map. Here I have given the scale. Temperature varies from 280 Kelvin to 327 Kelvin. So what we can see here is this portion along the river near the Mysore, Mandya districts, where people do a lot of very good irrigated agriculture. Like crops are grown with full extent through irrigation from this Kabini River basically. So here we are basically seeing a lower temperature. Temperature is in the order of 280 to 90 Kelvin because there is water, there is crop, and hence the temperature is slightly lower over the area. Whatever the energy coming in from the sun or earth is used to convert the water from liquid to vapor form, and the temperature is lower. On the other hand, here in this particular area, that is dry barren surfaces, temperature is higher because there is not much of water, not much of crop. Temperature is much higher. This particular portion, lower portion of this particular image is that is like Western Ghats or hilly regions with forest, plantations and all there. Essentially, since there is again a lot of vegetation, forest are there, its temperature is also lower. So basically, wherever we sense lower temperature, we will be seeing that is those particular areas will most likely correspond to areas with very good water content or good crop, and vice versa. If the temperature is dry bare, then definitely there will be higher temperature and all. So this is a one of the most commonly used example for thermal infrared remote sensing. Just for like to having discussions, I am stopping my lecture at this point because I don't want to go really technical, and those who are new, I don't want to create a kind of like a difficult image. So, but I'll be happy to take questions. So next remaining 15 minutes, we can have discussions, and whatever doubts you have, please ask me and I'll try to clarify to my best possible way.
Dear participants, if you have any doubts, you can raise your queries through the chat box available. Sir, there is one question like, can TIR be used for predicting land use dynamics of a region?
Yes, it is possible. Land use dynamics is, we can do it. Mostly people have tried it in annual scale or even like a five-year different kind of scale. So what essentially happens is we cannot pinpoint what land cover is there, but we can pinpoint whether the land cover is kind of vegetated or dry bare surfaces and so on. So we can study whether there is like urbanization or there is kind of deforestation occurred. So that kind of broad studies we can do, but we cannot pinpoint, okay, this is cropland, this is plantation. Like that we cannot classify like what we normally do. But we can still do some sort of land cover dynamics. People have done it and it is possible, yes. To some extent.
Okay, fine, sir. Another question is how to download or create TIR sensed images.
There are like different sources. Basically, the most common source for TR images, NASA Earth, NASA portal. Like I think NASA Earth now is there is a portal where we can download this thermal infrared data from multiple sensors like MODIS, Landsat, uh, VARS. These are some of the commonly used sensors. Just go search NASA Earth now tool. Once we register there, we can search for this data. We can download it. It will directly give us LST data, that is land surface temperature data. For Landsat, we don't have Landsat satellite. We have to create our own LST maps. That is like again a somewhat difficult problem, but still we can do it. For Indian sensors, like Indian sensor, we, as I said, we have INSAT 3D in geostationary orbit, which will give data at 5 km resolution every 30 minutes. That we can download from MOSDAC portal, MOSDAC. Maybe I'll type it in the chat box.
Okay, sir.
MOSDAC. Yeah, one second.
Okay.
Yeah, MOSDAC portal. If we can search, go to MOSDAC portal, register, we can download INSAT 3D data.
Okay, sir. The next question is how TIR will prove a beneficial use in remote areas for construction industries.
Construction industries as such, not for like a small construction projects, I will say, but as I said before, it will be useful for planners on a city scale. Let us say, like someone is working on developing a city, a new city is going to develop, then people can use thermal remote sensing to monitor how much heat is coming from the city as the city develops and how to reduce it. See, Chennai has developed much in the last, say, 20-30 years. So what is the transformation of the city and how to reduce its heat content? Basically, that we can do. So not for construction industry as such, but for planning purposes.
Sir, in thermal infrared remote sensing, we can observe the soil moisture loss, isn't it? So, what is the threshold you will fix in order to determine its soil loss?
Like soil moisture.
Yes, sir. You will determine soil moisture using TIR images, isn't it? What is the threshold value you will keep in order to evaluate its soil content, moisture content?
Okay, threshold value you're asking in terms of temperature, madam?
Yes, in terms of
Like
temperature.
what's the temperature? Okay.
No, sir.
Okay.
General moisture or water content, or in terms of water content also it is.
Okay. Soil moisture, yes, it is possible. Thermal remote sensing will give us, but normally the problem with thermal infrared remote sensing is it will give only the what we will see the skin temperature. Essentially, it will measure soil moisture from less than 1 millimeter thickness of the earth land surface, basically. So, but for most of the agricultural applications, people will need somewhat depth, say 5 to 10 centimeters at least. So that is the one of the major reason for going not for using thermal infrared remote sensing for soil moisture. We can do it, but it is not possible. That is not being normally done. Normally, people use passive microwave data for it. It's again related, but a different technology, but closely related with each other. That is one thing. Second thing is, there is no fixed threshold. There are different methods to get soil moisture from TIR remote sensing. It is possible, but based on each and every image over our region of interest, the temperature threshold will vary and the soil moisture that we can retrieve also will vary. It depends on different factors like the vegetation cover of the area, satellite sensors properties, or even the soil properties. So it is not a straightforward question to answer. We have to fix different thresholds based on our region of interest and the image that we have.
It also depends upon the temporal data, so seasonal changes, summer, winter. If there is any relation in the seasons with respect to season.
With respect to season, rather than season, I will say with respect to change in vegetation, I will say. Because like our vegetation pattern, our cropping pattern closely follows the seasonal cycles, but the presence of vegetation and the extent with which vegetation has grown will change the TAR signal. So I will say that these things, the soil moisture estimation will change with respect to vegetation.
So, what is the difference between MODIS data and Sentinel data? So now many people are using Sentinel data to measure soil moisture content. Isn't it? What is the difference?
That's possible. Sentinel. Okay. I think there are like commonly used, there are 3 Sentinel satellites we commonly use: Sentinel-1, 2, 3. Sentinel-1 is a radar satellite, active microwave data. Sentinel-2 is optical, very similar to MODIS and Landsat. Sentinel-3, again, it's a optical sensor, but it has its own TAR band. Like Sentinel-1 does not have a TAR band, Sentinel-2 does not have a TAR band, Sentinel-3 has it. So if we get soil moisture from MODIS, which has a TAR band, or if we can get soil moisture from Sentinel-3, they are related to each other using TAR data. But Sentinel-1 is using microwave data, active microwave radar data, and the way in which we measure soil moisture is entirely different. It's not one and the same. So that's entirely different physics. This is entirely different physics.
But which is the best component
So
of satellite imagery? Like Sentinel, we can go ahead, or we can, is there any comparative
there's
study?
no such best sensor, I'll say. No, I will not suggest just to take one sensor as satellite. As I said, Sentinel-1 with microwave has its own limitations. Say, for example, if the region is really cropped, then the radar may not work well. We have to go to different measures. So essentially, each sensor has its own limitation. So it is up to us to choose whether we are going to go for thermal data or if you want to go for microwave data. But for soil moisture applications, in general, people go for microwave data because of this depth penetration. I'll say one of the major reasons is the depth at which we can measure the soil moisture is slightly higher for microwave. That is why people mostly go for microwave data for soil moisture mapping. But the major problem with radar data is the data processing is really complex, and it's not a really straightforward to measure soil moisture from radar data. There's no base fixed model for doing it. The model is highly complex, and we have to do a lot of field measurements. Thermal data also is not really straightforward, but it's not as complex as microwave. So I won't suggest this is better than that. Each data has its own limitation, and its own advantage. So it is up to us to choose which sensor is best based on the data we have and based on the requirements we have.
Thank you, sir. Another question we can take, sir. Can we monitor water bodies like
sure.
lake using GIRS and influence of industrial waste and water pollution in it based on rate of evaporation?
We can monitor pollution, especially water bodies, from TAR data. And some really good examples are like whenever there's a effluent discharge, say some pollution is coming out from a thermal power plant, the particular effluent coming out will be at a completely different higher temperature than the water body. So there'll be a very good change in temperature that we can sense. If we can fly a drone or if we can fly a small aircraft fitted with a thermal sensor over the water body, we can very clearly see the change in temperature between the point at which the pollutant is let out and the normal water body. So thermal infrared remote sensing is useful for studying the water body pollution, and also the change of water body also can be seen. Like change in water body is areal extent. Say if there's a shrinkage in water body, then there will be a change in TR signal definitely. So that also we can sense. But only thing is current satellites will not be able to provide us. Current satellites are at a really coarse resolution. We need to go for drone-based surveys or something. We need to fix a TR sensor to a drone, fly over our region of interest and do it.
So another question, sir. What is the inference of calculating the evapotranspiration from the land or the semi-urban area or rural areas?
No, madam, the question is not very clear to me.
No, sir. We are calculating evapotranspiration through energy balance equation, isn't it, sir?
Yes.
Sir, evapotranspiration plays a major role in semi-urban area or a rural area.
That also depends on, say, what is the kind of vegetation present over here. Say rural area also need not be completely cropped or with full of vegetation, right? Rural area, it can be dry, barren. Say if you go to our dry district, some of the rural areas in Sivaganga district, Ramnath district are all extremely dry. Not much of crops are present, so not much of evapotranspiration will be going on. But if you go to somewhat semi-urban areas, like if you go just outside Chennai and between like transition zones between Chennai, Chengalpattu and all, we can see some amount of agriculture going on. So there ET will be higher. So really it is not between semi-urban, rural and urban. It is basically how much water is present. Even over urban areas, people can grow vertical gardens, water the plants, evaporate more water. Actually, like in there is a good story about Los Angeles, which is one of the highly urbanized area in the world, like in US, Los Angeles city. Los Angeles basically is a desert without much water over it. But because of urbanization, people living in Los Angeles are most of the people are rich. They have their own houses, big lawns, and they water the lawns every day. So what has happened is, instead of being really dry, because of urbanization, some areas of Los Angeles has become cooler because of this lawn and regular watering. So urbanization can also change the characteristic of landscape. So what I wanted to tell is, it is not urban, rural and all, it is the presence of water and vegetation which will change the thermal signature. So even in urban areas can be cooler, but rural areas also can be drier and hotter. That's what I wanted to tell.
Okay, sir. In the case of our Chennai city contest, we have a forced reservoir, but the water bodies have been enclosed since 2 decades. So the evapotranspiration will increase, isn't it, sir?
Sorry, ma'am. Can you please repeat the question?
No, sir. If the
We have
temperature
reservoirs.
in the reservoirs at the present scenario in Chennai, if the water body is being encroached due to urbanization, will the transpiration process will increase or it will decrease, sir?
Okay. When the water body shrinks, evapotranspiration will decrease. ET will decrease. Basically, when the water body is encroached, water cannot be stored. It will be converted to buildings. Naturally, ET will decrease. Temperature will increase.
But urban heat effect will increase, isn't it, sir? If the water body moisture is not available, then the heat waves will be produced more, isn't it?
Yes. Temperature will increase. Yes, that will happen.
So how, what I mean to say, this temperature kind of study is really useful for what kind of application? So like the inference of a ET should be like for a water solution we have to take. Like what is the inference out of the ET studies?
As I said, it depends on the real application. Maybe like I'll tell one example. Like when I was doing my BE, I did a small minor project in which I tried to calculate this temperature of Chennai city. Basically, that was the first project I did in thermal remote sensing.
Okay,
there I can clearly see between 2000 and I think 2009 image I used. Then at that particular point, I can see there's a change in this Pallikaranai marshland because it was being enclosed, it is being urbanized that particular time. I can see a difference in surface temperature as well as surface emissivity. As the Pallikaranai marshland being vegetated, when new buildings are being built, its emissivity changed as well as the temperature increased. So that is one real example of urbanization, change in temperature and change in surface emissivity. That is one application. I had not studied evapotranspiration at the time, but just by looking at temperature, I can see like, okay, the marshland has shrunk. That is possible, yes.
So what is the difference between water balance equation and energy balance equations?
Okay, madam. Water balance, it is how water is coming in out of an area. That is water balance equation. Water in and water out, how it is balancing. Energy balance is same thing. How much energy is coming in and energy is going out. These two are linked by evapotranspiration, basically. Like in water balance term, one of the way in which water can be lost is ET, evapotranspiration. For evapotranspiration to occur, some energy will be taken up. So energy cycle and water cycle, they are completely different cycles. They are linked together by the process of ET.
So what is like that evapotranspiration? It can be like 400 mm per hour, isn't it? So for a month, or like 8 mm per day, isn't it? The permissible evapotranspiration from the landscape.
No. Again, it depends on the land cover. Say based on the water body, based on crop. Say if there is like a lake or something that is really deep and it is standing, then the evapotranspiration can be much higher in the order of say 100-200 millimeters per month. It can keep on occurring. And if there is like a crop like sugarcane or paddy, it can give out lot of water in evapotranspiration. Like for sugarcane, I think the water requirement is something around roughly 150 millimeters per month or 1800 millimeters per year. For some other crops like dry crops like cereal pulses, it will be much lower. So it depends based on the crop or the water content of the area. So it's not a fixed value. the value changes with respect to the crop present.
Okay, thank you, sir. I cleared my doubts. It was a very nice presentation, sir. We liked your presentation. It was very quite informative. The basics of remote sensing and basics of thermal remote sensing. The participants might have enjoyed your lecture, and I'm very glad to invite you for this section, sir. Now I call upon Dr. Gopal Krishnan, sir, senior professor of our department, to deliver a vote of thanks.
Thank you, madam. Yeah.
Okay, welcome.
Good afternoon, sir. Again, good afternoon. On behalf
good
of our
afternoon, sir.
Department of Civil Engineering, thank you for your valuable speech and spending your time also. This was a very informative session, and more faculty members and the students will be benefited by this session. Thank you once again, sir. Thank you.
Yeah, thank you, sir. Thank you for giving me the opportunity. And if some faculty members or students are really interested in it, please feel free to write to me. Whenever I find time, I'll definitely reply back. You can always email me, no problem.
Yes, sir. We'll be regularly in touch with you for further future for our any programs or any bilateral projects development, everything, sir. Thank you.
Sure, sir. Happy to join you.
Yeah. Thank you for spending your time.
Sir.
Thank you.
Thanks,
Priya, madam.
Okay, yes, sir. Yes, sir. I'm on the line, sir.
Yeah, I think we can close the session now. Yeah.
Okay, sir.
Yeah.
Okay, sir.
Thank
We
you,
can.
madam.
Okay, sir. We can. Thank you, sir.
Okay, madam. I'll also leave the meeting. Yeah, thanks. Bye.
Thank you.
Thanks, sir. Thanks, dear participants. It's lovely to see you all. Thank you for attending this webinar. I'm thankful to everyone who has given me this opportunity to conduct this webinar. Once again, I thank everyone for attending this webinar.